In this section, we're going to look at how to find the arc length, or S, and also how to find the area of sectors. Now, what we've already looked at is our definition for our central angle in radians. We have a central angle theta. Then, if you remember, theta was defined to be the arc length, the distance traveled on the edge of the circle, divided by the radius. So if we use our algebra and we multiply both sides by the radius, then we get that the arc length is equal to r times theta, where theta is in radians. So this allows us then, given the radius and our central angle of rotation in radians, then we can find the distance that's traveled. So we have a formula for that. If theta in radians is a central angle in a circle with radius r, then the length of the arc cut off by theta is given by S is equal to r times theta. So let's look at a few problems where we can find then our arc length. If our central angle is 2 radians and our radius is 4.2, then our arc length is going to be equal to 4.3, I think I said 4.2, times 2, which would give us 8.6, and that would be inches. This is a length, and we give our lengths in units of length. And remember, we don't really deal with the radians. We don't have to keep track of that in our problems. It's letting us know that this is a real number. So what we had to do was keep track of our units of length. Okay, let's look at this problem. And the difference in this problem and the one that we just did is that our central angle is given in degrees. So what we're going to have to do is change these to radians. Now, 45 degrees is one you're supposed to have memorized in radians. But if you've forgotten that, or we just need to go through it, then remember we multiply this by pi over 180. To change degrees to radians, we're wanting to get rid of the degrees. And so 45 goes into 180 4 times. So 45 degrees is pi over 4 radians. So we can find our arc length is equal to r, which is 125 feet, times pi over 4 radians, which gives us 125 pi over 4 feet. Now that's an exact answer. And if you were going to then use it in another part of a problem, you would want to keep it exact. But if we're going to go out and measure that, that really doesn't give us any meaning. So we need to go to our calculator and get an approximation. Now, since we're not trying to find trigonometric functions of our angle, it doesn't really matter if our calculator is in the degree mode or the radian mode, because we're just multiplying by real numbers, which is what radians are. So, but if you want to, you can change your mode to the radian mode if you want to put it in that mode, but it really doesn't matter in this case for the computation. So we have 125 pi divided by 4. So that gives us approximately 98 feet or 98.2 feet. Now to show that it's approximate, remember we use those little wavy lines, 98.2 feet. Okay, let's look at another problem. Say that we're given our central angle in radians and we have a radius of 4. Then our arc length is simply our radius, 12 centimeters, times pi over 3. We can cancel, and we end up with 4 pi. 4 pi centimeters. And again, if you were going to measure that, that doesn't have a lot of meaning for us. So we could go back to our calculator and do 4 times pi and get approximately 12.6 centimeters. So if we're given our central angle in either radians or degrees and the radius, then we can find the arc length that's cut. We could also, if you wanted to, and I've seen this, probably you've actually seen this back in your geometry uh, classes, because at that point you hadn't dealt with radians. So sometimes what you may want to do is just put that conversion inside your problem. So we have our radius, which is 4, then times our central angle, which is 30 degrees, and we want to change that to radians, which is pi over 180. And you may have actually seen that as a formula back in geometry because you mainly dealt with degrees there. So now we could cancel, and we've got pi over 6. We could cancel here. 2 goes into 4, 2 goes into 6, and so we end up with 2 pi over 3 inches. And we could get an approximation on our calculator. 2 pi, whoops, divided by 3. So approximately 2.1 inches. All right, we've got one more problem here. And on this problem, notice we're given the arc length and the central angle, and we want to figure up what our radius is. Well, if we go back to our formula, our arc length is equal to our uh, radius times our central angle. So if we divide our arc length by our central angle, we would have our radius. So our arc length was 230 divided by, now it was in degrees, so we went ahead, we just did this while ago. 45 is pi over 4, which is, again, that's one that we know. Okay, to divide by a fraction, you multiply by the reciprocal, 4 over pi. So we end up with 920 over pi, and that would be feet. Well, we don't know what that is, so if we go, we would have 920 divided by pi, which is approximately 293 feet. Not wanting to stay there. Okay, 293 feet is what we would get there then as our approximation for our radius. So you can use your formula in several different ways. So that's finding our arc length. Now, there are some typical types of problems that we have where we're using our arc length to find some things. Let's look at a couple of these, and then we're going to look at finding the area of the sector. So if we have this one, it says that the minute hand of a clock is 4.5 centimeters long. How far does the minute hand travel in 20 minutes? Well, this doesn't give us the central angle. But we know that a minute hand, if we start out at 12 and we travel for 20 minutes, we would be around about here. And so we've actually gone 20/60ths of a rotation. All the way around would take us 60 minutes, so we've gone for 20 minutes. So we've gone 1/3 of a rotation. We know that a full rotation is 2 pi radians. So we've gone 1/3 of 2 pi, or 2 pi over 3 radians. So now we know what our central angle is. It was our amount of rotation times the 2 pi, which is a full rotation. So we have a central angle now, so we want to know the distance, and that would be our radius, which is 4.5, times our central angle, 2 pi over 3. And if we get an approximation of that, then we've got 4.5 times 2 pi divided by 3. So approximately 9.4 centimeters. That should just be a cm. 9.4 centimeters would be the distance that the tip of the hand traveled as it went around our clock. Now we can use this also to measure very long distances. Let's look at this problem. It says from the Earth, the moon subtends an angle of approximately 5/10 of a degree, half of a degree. If the distance to the moon is approximately 240,000 miles, find an apparent diameter of the moon. So if we have our moon way out here, and we're looking from Earth. So we're down here on the Earth and we're looking up at the moon through a telescope probably. And we find that if we look to one side of the moon and then move our view to the other side of the moon, then that subtends an angle here of half of a degree. Now we're trying to get the diameter. What we have is a formula for an arc length. But if the distance is far enough away, the difference between a straight line there and the curve on the arc is very little. And so this is why it's called an apparent diameter, is because that's what the diameter appears. The arc length for that small of an angle over this large distance of 240,000 miles, there's not going to be much difference between the straight line diameter of the moon and that small curve for our arc. So we can use our formula that the arc length is equal to r times theta. Well, our r is 240,000. Now theta is in degrees, so we can say it's half a degree. So we could actually use 1/2, or we can use the 0.5. I'm going to use the 1/2 times, and we want to change this, times pi over 180. And I'm just going to put that into my formula. So I'm not even going to worry about canceling here because I'm going to use the calculator anyhow, and these are huge numbers, although we could cancel there. We've got 240,000 times pi over 360. So if we go to the calculator, we have 240,000 pi divided by 360. So the diameter of the moon is approximately 2,094 miles. $2,094. And you would probably say over that distance that it has an approximate diameter of 2,000 miles because we've approximated the length, the distance, and this is just apparent. So, if you 2,000 would be a close enough answer. But this is what we call apparent diameter. And so this is giving us a way to measure things that are very far away. All right, let's look at another section that deals with the sector area of a sector. Okay, we want to look at finding the area of just a sector of a circle. And we know from arithmetic and geometry that if we wanted to find the area of the whole circle, our formula is pi r squared. But we don't want the whole circle, we just want a portion, the area of this sector. And so let's set up a ratio that the area of the sector that we're trying to find is to the area of the whole circle, as the central angle of that sector is to the central angle for the whole circle, which we know is 2 pi. Now, if we took this and we multiplied both sides by pi r squared, we want to solve for the area. So we're going to multiply both sides by the denominator by pi r squared. Then this will cancel and we get that the area of the sector, well, my pi's cancel, and I have 1/2 theta times the radius squared. And again, theta is in radians. So this gives us then the formula to find the area of a sector of a circle. If theta in radians is a central angle in a circle with radius r, then the area of the sector formed by angle theta is given by 1/2 r squared theta. So if we have a circle and our central angle is 1.4 radians and our radius is 2.1 meters, then we can find the area of that sector. It's equal to 1/2 the radius squared, 2.1 squared, times the central angle, 1.4 radians. And so that was 2.1, it's a little hard to read. Okay, let's use our calculator then to find an approximate area. So we could use 0.5, 1/2, times 2.1 squared times 1.4. And we get 3.087, approximately that, 3.087. Now, let's look at our units. This 2.1 was meters, and so when we squared this, then we have meters squared. Anytime you're doing area, your units are going to be in square units. Okay, let's look at another one. Let's say that our central angle was 3 pi over 4 radians, and we are given an arc length of pi centimeters. Now, our formula for area was 1/2 the radius squared times the central angle. But we're not being given the radius here. We're given the arc length. Well, if you remember our arc length formula, that was equal to our radius times our central angle. So our radius is equal to our arc length divided by theta. And we actually did that in some of our problems. Now, that's what we have here. We could go through and we could figure that up. We could say, well, r is equal to pi over 3 pi over 4. which is the same as pi times 4 over 3 pi. Pi's cancel and we get 4/3 centimeters would be what our uh, radius would be. We could also, so we can substitute in 4/3 there. And then our central angle is 3 pi over 4. So we have 1/2 times 16/9 times 3 pi over 4. And we can do some canceling. 4 goes into 16 4 times. 3 goes into 9 3 times. And 2 goes into 4 2 times. So we end up with 2 pi over 3, and that would be centimeters squared. And we can get us an approximation. 2 pi divided by 3. So approximately 2.09 centimeters squared. So when we weren't given the radius, we were still given enough information to find it. Now, once we found this part, that the radius is s over theta, we could have just put all of that into the formula here, but it would have been a little messy having all of this and squaring it. We would have still had to have done the computation. So we can find then the area of a sector. Let's say that we were given our central angle in degrees. Then we're going to have to change that. Again, you can put that in the problem, or you can do it off to the side by pi over 180. So 15 goes in there once, 15 goes in here 12 times, so it's going to be pi over 12 radians. So our area is equal to 1/2 our radius of 10 times pi over 12. And canceling, we get 5 pi over 12 would be an exact answer, meters squared. An approximate answer would be 5 pi divided by 12. So 1.3 meters squared. And that gives us then ways of finding the area of sectors. So this is basically looking then at two formulas. One dealt with arc length, and arc length is equal to the radius times the central angle in radians. We have to have that central angle in radians. And then our area of a sector, where it's equal to 1/2 r squared theta.